Hey everybody, please forgive the pack or stack, not pack of recycling over there, but this is a quick video over one of the basics of neurotransmission that I've received a question about, specifically excitation and inhibition. Now, to understand the concepts of excitation and inhibition, we have to put in the right context. So usually we're only talking about excitation and inhibition when we're talking about neural activity. And that neural activity could be a receptor, like the cones and rods in the eye. It could be a bipolar cell, like in the eye or in the nose. It could be a ganglion cell. And every cell in your body, or sorry, every neuron in your body experiences excitation or inhibition. Now, not every cell, not every neuron in your body experiences what is called an action potential, which is a abrupt spike in charge or an abrupt change in polarization, but we'll get to that in a second. So to help everybody visualize this, I'm going to share the screen. Boom. All right, let me just double check that. Sorry, guys. Okay, so to start off, we have to understand a resting potential. Now, imagine a neuron, okay? Here's several neurons. You've got unipolar neurons, bipolar neurons, and multipolar neurons. Now, unipolar neurons are like your receptor cells, like your rods and cones. Those are unipolar. You got bipolar neurons, like the ones in your retina and nose, and then you got your multipolar neurons, and those are spread throughout your body. And the principal difference between each of these classes of neuron is how many extensions proceed from the body, from the cell body. All right, so with unipolar you've got one extension, bipolar you've got two, and with multipolar you've got one major extension known as the axon, and then you've got multiple dendrites. Now, with these neurons, they are electrically charged, all right? And the reason for that is because there are more negatively charged ions on the inside of the cell than there are on the outside. And that gives the membrane of the cell a charge. That charge is the resting potential. So the charge of the cell, when nothing is happening to it, when it's not receiving any input or anything, when that charge of the cell is known as the resting potential. Now, the resting potential is maintained by a number of things, but we won't go into that in this video. Your book talks about it, but if you would like further, more coverage of that, just let me know. Now, so a resting potential, on average, although it differs across each of the cells, on average is about negative 70 millivolts, all right? Meaning that the inside of the cell is negative 70 volts, more negative in polarization than the net charge outside the cell. Now, it's maintained because of things like your sodium-potassium pump, but like I said, that's not the focus of this video. Now, keep in mind that your resting potential, again, is the net charge of the membrane when nothing's happening to the cell. But here's the thing about most of your cells. Most of your cells, especially the multipolar neurons, they are never not active. Every cell has what's called a spontaneous firing rate, meaning it fires at a random rate. And so really what we're talking about is anything that increases that firing rate or decreases it. But the resting potential, again, is the charge across the membrane of the cell, of the neuron's cell body when it's not receiving any input. Well, when we talk about excitation and inhibition, what we're talking about are things from outside of the neuron, maybe neighboring neurons, that are changing the potential of the neuron. And so this can happen because in the membrane of the cell, you've got these little channels, these little gated channels, all right? And they're called gated channels because different things will open them. A channel is like if you think about a channel that boats go through, all right? It's closed off, and then when you open it, the boat can go through. Well, that's exactly what a channel is with the membrane. All right, you've got these channels, you've got these ports. Well, not really a port, but these openings that are closed, and they're gated, meaning they have something like a key. Well, usually the key is a ligand or a chemical, and that chemical can be a neurotransmitter or some other chemical floating around in the system. But what matters is whether or not that chemical's molecules have the right shape, because the molecule acts like a key. All right. So if you have, so some of these channels are gated, meaning their locks can only be opened by chemicals, and those are called ligand-gated channels. You have others that other channels that are closed, and they can only be opened when the polarity of the cell changes. Okay, so let's go back to the ligand-gated channels. Those ligand-gated channels operate on a key and lock principle, meaning that only if the molecule with the right shape comes along and connects to the receptor that gates the channel on a ligand-gated channel, only when the right molecule with the right shape comes along and connects to that receptor will that channel open. Now, when that happens, that channel will open and it can let sodium in, and sodium's a positively charged ion. Well, if sodium comes in, a positively charged ion comes in, what's it going to do to a charge of negative 70 millivolts? Anyway, what is it going to do to a charge of negative 70 millivolts? It's going to move it closer to zero. All right. So, as a quick aside, you can think of zero as no polarization whatsoever, but movement in either direction from zero, over zero to hyperpositive, or below zero to hypernegative, as polarization. So anytime you move away from a pole towards zero, that's depolarization. And anytime you move away from zero to a pole, that's hyperpolarization. All right. So if a molecule comes along, opens up a channel that allows sodium inside, and sodium's positively charged, it adds a positive 1 to negative 70, moving it to negative 69, meaning it's moving closer to zero, meaning it's depolarizing. So if the right molecules come along, open up the right channels, sodium comes in, it can depolarize the neuron. Other channels might let negatively or force negatively charged ions in, or positively charged ions out. In effect, anything that when sodium or other charged ions move across the membrane, if that movement makes the inside less negative, that's a depolarizing effect. If it makes the inside more negative, that's a hyperpolarizing effect. Now, why do these things matter? Well, in cells that have a action potential, oh, so here's a picture of some neighboring cells sending chemicals that might open those ligand-gated channels. But in cells with action potentials, here's your resting potential. If something comes in and opens up a channel and lets positive charges in, you get movement up. Well, why does that matter? Well, every cell with an action potential has a threshold of excitation. If a cell is depolarized enough to reach the threshold of excitation, the action potential is charged or activated, and you get this massive positive spike in the charge of the axon, in the charge of the neuron. Now, there are other cells like your receptors and bipolar cells, they don't have action potentials at all. And so if something comes in and lets sodium in, or prevents or kicks a positively charged ion out, all right, then all we get is movement in the activity of the cell, and it either does more of what it always does or does less of it. But that's a topic for a different time. So if an incoming effect depolarizes a cell, it usually means it's usually going to do, that depolarizing effect is usually going to make that cell do more of what it was going to do. So if it's a cell with an action potential, then incoming ions that depolarize the cell move the cell towards its threshold of excitation, which you can see right here, and make it more likely to achieve an action potential. When a cell achieves its action potential or does more of what it would ordinarily do, it's said to be excited. All right. So when we say that something has an excitatory effect, what we're saying is that it's making a cell more likely to fire if it has an action potential, or more likely to do its thing. So like your receptors, when they're excited, they release glutamate. All right. So something that depolarizes the receptors makes them more likely to release glutamate. Cells that have action potentials, the more excited they are, the more likely they are to achieve an action potential. Well, remember that some ligand-gated channels actually hyperpolarize the neuron. They let negative ions in or positive ions out, making the -70 move further away from 0. And remember that when we move further away from 0, we're hyperpolarizing. Well, when you hyperpolarize a cell, you make it less likely to do what it was going to do. So if it's a cell with an action potential and you hyperpolarize it, you make it less likely to do what it was going to do, then you are inhibiting it. You're making it less likely. You're inhibiting it from achieving an action potential. If it was a receptor, if you were inhibiting a receptor, you would make it less likely to produce glutamate. Glutamate is a neurotransmitter. All right, so that is what we mean by excitation and inhibition. Excitation is when changes from the outside of a cell make that cell either more likely to fire, and by fire I mean achieve an action potential, or produce more of what it naturally produces, like receptors producing glutamate. An inhibitory effect is when signals from the outside come in and make it less likely to fire, meaning less likely to achieve an action potential, or less likely to do what it was produce what it was going to produce, like receptors. If something inhibited a receptor, it would be less likely to produce glutamate, or it would produce less glutamate. And that is the concepts. Those are the concepts of excitation and inhibition. I hope this video has helped. If there's any questions from this video, please let me know. If not, see you later on.